Hi, I'm Alex. Tonight we're talking about spacetime, the thing that holds the universe together, powers GPS, bends light, and traps black holes. Scientists use it every day. They can measure it, stretch it, even photograph it. And yet, here's the unsettling truth. We understand how spacetime behaves, not what it is. It's a journey into modern physics' deepest questions, where space and time begin, where they fail, and why answering them could change reality itself. If journeys like this ignite your curiosity, I'd be grateful if you subscribe to the channel so this journey can continue to grow and quietly offer more value. Now let's begin. Space-time can be bent, stretched, rippled, even torn apart. But here's what nobody tells you. Nobody knows what it actually is. Let me show you the evidence. September 14th, 2015. The Laser Interferometer Gravitational Wave Observatory, LIGO, detected something extraordinary. Space-time itself was vibrating. The amplitude, 1/10,000th, the width of a proton. Think about how small that is. A proton is already tiny, about 10 to the minus 15 meters across. This vibration was 10,000 times smaller than that. LIGO measured spacetime shaking with an amplitude so small it defies imagination. What caused it? Two black holes, each about 30 times the mass of the Sun, colliding 1.3 billion years ago. When they merged, the collision released more energy in a fraction of a second than all the stars in the observable universe emit in the same time. About 3 solar masses worth of energy, the equivalent of annihilating 3 suns, and converting all their mass directly to energy radiated away as gravitational waves in less than a second. Those waves traveled through space at the speed of light for 1.3 billion years. When they reached Earth, they stretched and squeezed the 4-kilometer arms of LIGO by about 1,000th the width of a proton. And LIGO detected it. We caught spacetime ringing like a bell. Now jump to 2019. The Event Horizon Telescope, a network of 8 radio telescopes spread across the entire planet from Hawaii to Antarctica, from Spain to Chile, captured something never seen before, an actual photograph of light being bent around a black hole. The target was M87 star, a supermassive black hole at the center of the galaxy, Messier 87, about 55 million light-years away. This black hole weighs 6.5 billion times the mass of our Sun. The image shows a ring of glowing orange light surrounding absolute darkness. That dark circle in the center of the shadow has a diameter of about 40 billion kilometers. That's about 3 times the size of Pluto's orbit around the Sun. The ring of light is gas orbiting the black hole at speeds approaching the speed of light, heated to billions of degrees. But here's what's remarkable. The light from that gas has been bent by space-time. Photons that should travel in straight lines are forced to follow curved paths because the fabric they're moving through is warped. Some photons orbit the black hole multiple times before escaping. You're looking at a direct photograph of curved space-time, not an artist's interpretation. Real photons that traveled millions of light years to reach us. Or consider something you probably used today: GPS. Your phone, your car's navigation system, any device that tells you where you are, uses satellites orbiting Earth about 20,000 kilometers up. These satellites constantly broadcast signals containing the exact time and their positions. Your GPS device receives signals from at least 4 satellites, measures how long the signals took to arrive, and calculates your position. But there's a problem. Time runs differently at different heights. The satellites are higher up in Earth's gravitational field. They experience weaker gravity. According to Einstein's theory, time runs faster in weaker gravitational fields. The satellite clocks gain about 45 microseconds per day compared to clocks on the ground. But there's also another effect. The satellites are moving at about 14,000 kilometers per hour relative to the ground. According to Einstein's special relativity, time runs slower for moving objects. The satellite clocks lose about 7 microseconds per day. Add these together. The satellite clocks run about 38 microseconds per day, faster than clocks on the ground. That doesn't sound like much, but light travels about 300 meters in 1 microsecond. If GPS didn't correct for these effects, your position would be off by about 11 kilometers per day. Within hours, GPS would be completely useless. Your navigation would tell you you're in the wrong city. Every time you use GPS to navigate, you're relying on corrections for the curvature of spacetime. It works. It works perfectly. So here's the reveal. We can measure spacetime. We've photographed it. We've detected it vibrating. We use it every single day. And yet nobody can tell you what it actually is. We don't know what it's made of. There are 3 big mysteries, 3 questions at the edge of human knowledge. First, what is spacetime made of? At the smallest scales, what is this fabric actually composed of? Second, what happened at the Big Bang? When spacetime itself began, what actually occurred? Third, do black holes destroy information? When something falls into a black hole, is the information about it lost forever? These aren't just abstract physics questions. They're questions about the nature of reality itself. You're living in space-time right now. You're breathing in it, moving through it. Every step you take, every breath, every heartbeat happens inside this thing we call space-time. But what is it Einstein created this concept in 1915? It's been 110 years. We've tested his theory thousands of times. It's never failed. We've built technologies around it. We've used it to predict the existence of black holes, gravitational waves, the expansion of the universe. Everything Einstein predicted turned out to be true, and yet we still don't know what it actually is. It's like discovering you've been living inside the Matrix your whole life, but you can't figure out if it's running on Windows or Mac OS. You can see the effects, you can measure them, you can use them, but the fundamental nature of the thing itself remains hidden. To understand why this is such a mystery, why physicists have been struggling with this for over a century, you need to understand how Einstein invented space-time in the first place. You need to see how he went from a 26-year-old patent clerk to revolutionizing our understanding of reality itself. And you need to see where his beautiful theory leads to places even Einstein himself refused to believe were real. Let's start in 1905. Albert Einstein was 26 years old, working as a patent clerk in Bern, Switzerland. He wasn't a professor. He didn't work at a university. He examined patent applications for electromagnetic devices during the day and thought about physics at night. And in that year, 1905, he published 4 papers that would change physics forever. One explained Brownian motion and proved atoms were real. One explained the photoelectric effect and helped establish quantum mechanics. And 2 papers introduced what we now call special relativity. Special relativity sounds complicated, but the core idea is actually straightforward. Einstein realized that the speed of light is always the same, no matter how fast you're moving. Always 300,000 kilometers per second. About 186,000 miles per second. The same speed for everyone. This seems impossible at first. If you're on a train moving at 100 kilometers per hour, and you throw a ball forward at 20 kilometers per hour, someone standing on the ground sees the ball moving at 120 kilometers per hour. The speeds add up. That makes sense. That's what we expect. But Einstein showed that light doesn't work this way. If you're on a spaceship moving at half the speed of light and you shine a flashlight forward, you might think the light would move at 1.5 times the speed of light from the perspective of someone watching you, but it doesn't. The light moves at exactly the speed of light, 300,000 kilometers per second, both from your perspective and from the perspective of someone watching you from outside. The same speed. Always. This seems impossible. How can light be moving at the same speed for both observers when one observer is already moving at half the speed of light? Einstein's answer was radical. Space and time adjust to keep the speed of light constant. If you're moving very fast, time literally runs slower for you from the perspective of someone standing still, and distances in the direction you're moving actually contract. They shrink. These aren't optical illusions. They're real physical effects. Time and space are not absolute. They're relative depending on your motion. The only thing that's absolute, that's the same for everyone, regardless of how they're moving, is the speed of light. This was shocking. In 1905, it overturned centuries of assumptions about how the universe works. Newton had built physics on the idea that time flows the same for everyone, that a second is a second, no matter where you are or how fast you're moving. Einstein showed that wasn't true. Time is flexible. Space is flexible. They bend and stretch depending on your motion. Think about what this really means. If you could build a spaceship that travels at 99% of the speed of light, and you took a journey to a star 10 light years away and back from your perspective on the ship, the journey might only take a couple of years. But when you return to Earth, 20 years would have passed. Your friends would be 20 years older. Your children might now be older than you. This isn't science fiction. This is what Einstein's equations predict, and it's been confirmed by experiments countless times. We've tested this with particles in accelerators, unstable particles that normally decay in microseconds live much longer when they're traveling at 90.9% of light speed. We've tested it with atomic clocks on airplanes. When you fly an atomic clock around the world and compare it to an identical clock that stayed on the ground, the traveling clock shows less time has passed. The difference is tiny, just a few hundred nanoseconds, but it's measurable, and it matches Einstein's predictions exactly. The implications are profound. There's no universal, now no cosmic clock ticking at the same rate everywhere. When you say something is happening right now on a distant planet, that statement has no absolute meaning. Different observers moving at different speeds would disagree about what right now means. Time is not a river flowing at a constant rate for everyone. It's more like a fabric that can stretch and compress depending on how you're moving through it. But Einstein wasn't done. Special relativity only dealt with objects moving at constant speeds. It didn't handle acceleration, it didn't handle gravity, and gravity was a problem. Newton's law of gravity had worked brilliantly for over 200 years. You could use it to predict the motion of planets, the trajectory of cannonballs, the orbits of moons. It was one of the most successful theories in the history of science, but Einstein realized it couldn't be right. Not completely. Newton's gravity worked instantly. If the sun suddenly disappeared, Earth would immediately fly off into space. According to Newton's equations, the gravitational pull would vanish instantly across 150 million kilometers of empty space. But Einstein had just shown that nothing can travel faster than light. No signal, no force, no information can cross space instantly. If the sun disappeared, it would take about 8 minutes for the light to stop reaching Earth. That's how long light takes to travel from the sun to us. And Einstein realized gravity couldn't work any faster than light either. This led Einstein to one of the most productive thoughts of his life. He called it the happiest thought he ever had. It came to him in 1907. He was sitting in his office at the patent office thinking about gravity when he imagined a worker falling off a roof. While the worker is falling, Einstein realized the worker doesn't feel their own weight. They're weightless. They're in free fall. If they dropped a hammer while falling, the hammer would float next to them, falling at the same rate. They wouldn't see the hammer accelerate away or toward them. It would just hover there in midair from their perspective. This seems obvious now. We've all seen footage of astronauts floating in the International Space Station. But Einstein realized something profound. The worker falling off the roof and the astronaut floating in space are experiencing the same thing. They're both in free fall. The astronaut isn't actually floating in zero gravity. They're falling toward Earth just like the worker, but they're also moving sideways fast enough that they keep missing Earth. They're in orbit, continuously falling, but continuously missing the ground. And that's why they feel weightless. Not because there's no gravity, but because they're in free fall. Einstein realized that being in free fall is indistinguishable from being in empty space with no gravity at all. And being in a rocket accelerating upward is indistinguishable from standing on the surface of a planet feeling gravity pull you down. You can't tell the difference. If you're in a closed room with no windows, there's no experiment you can do to determine whether you're sitting on Earth's surface feeling 1 g of gravity or sitting in a rocket in deep space accelerating upward at 1 g. The effects are identical. This is called the equivalence principle. Acceleration and gravity are equivalent. They're the same thing. And this was the key insight that led Einstein to his theory of general relativity. If acceleration and gravity are the same thing, and if special relativity says that acceleration affects space and time, then gravity must also affect space and time. Gravity must curve space and time. It took Einstein another 8 years to work out the mathematics. From 1907 to 1915, he struggled with the equations. He learned advanced mathematics he'd never studied before. He worked with his mathematician friend Marcel Grossman. He made mistakes published wrong, results corrected them, and tried again. It was the hardest work of his life. But in November 1915, he finally got the equations right. He published his theory of general relativity and physics would never be the same. The field equations can be written compactly as g equals 8 pi t, where g is the Einstein tensor describing the curvature of spacetime, and t is the stress-energy tensor describing the distribution of mass and energy. Mass and energy curve spacetime, and objects moving through curved spacetime follow curved paths. That's what we experience as gravity. Earth isn't being pulled by the sun. Earth is moving in a straight line through spacetime, but the sun's enormous mass curves spacetime around it. Earth is trying to move straight, but the curved spacetime forces it to follow a curved path. That curved path is Earth's orbit. We experience this as the sun's gravity pulling on Earth. But from Einstein's perspective, there's no pull at all. There's just Earth moving through curved spacetime. This is the moment when space and time stopped being two separate things. They merged into a single fabric. Spacetime, 4 dimensions, 3 of space, and 1 of time woven together. And this fabric doesn't curve in some higher dimensional space. It curves in on itself. Mass and energy tell spacetime how to curve. Spacetime tells mass and energy how to move. And the first test of this radical new idea came from an eclipse in 1919, May 29th, 1919. There was a total solar eclipse. 2 expeditions set out to test Einstein's prediction. One, led by Arthur Eddington, traveled to the island of Principe, off the coast of West Africa. Another traveled to Sobral in Brazil. Their mission was simple but profound. Photograph stars near the sun during the eclipse. Einstein's theory predicted that starlight passing near the sun would be bent by the sun's curved spacetime. The stars would appear to shift position slightly when the sun was nearby, but you can't normally see stars near the sun. The sun is too bright. It drowns out the starlight. You can only see stars near the sun during a total solar eclipse, when the moon blocks the sun's light. Both expeditions photographed stars during the eclipse. They measured the positions of stars near the sun and compared them to the positions of the same stars photographed at night when the sun wasn't nearby. The stars had shifted. Light had been bent by the sun's gravity exactly as Einstein predicted. The measurements matched Einstein's equations. When the results were announced in November 1919, Einstein became an overnight celebrity. Newspapers around the world ran headlines about the eclipse results. Einstein's face appeared on magazine covers. He was invited to give lectures everywhere. He went from being a respected physicist to being the most famous scientist in the world. But this wasn't just about fame. General relativity had other successes too. It explained something that had puzzled astronomers for decades: the orbit of Mercury. Mercury, the closest planet to the Sun, has an orbit that's slightly off from what Newton's equations predict. The point where Mercury is closest to the Sun shifts very slightly with each orbit. This is called the precession of Mercury's perihelion. Astronomers had known about this for years and couldn't explain it. Some thought there might be another planet closer to the Sun than Mercury, pulling on it and causing the shift. But Einstein's equations predicted the exact amount of precession without needing any extra planets. Spacetime was curved more strongly near the Sun, and that extra curvature explained Mercury's strange orbit perfectly. By 1922, everyone in the physics community agreed. Einstein had solved gravity. The problem was closed. The theory was complete. And we use this theory every single day. Remember GPS. Let's dig deeper into why it needs Einstein. The satellites are orbiting 20,000 kilometers above Earth. At that height, gravity is weaker. According to general relativity, time runs faster in weaker gravitational fields. The satellite clocks gain about 45 microseconds per day compared to clocks on the ground. That's the effect of curved spacetime. But there's also the effect from special relativity. The satellites are moving at about 14,000 kilometers per hour relative to the ground. According to special relativity, time runs slower for moving objects. The satellite clocks lose about 7 microseconds per day. Add these together. The satellite clocks run about 38 microseconds per day faster than clocks on the ground. Engineers program the satellites to account for this. Without these corrections, GPS would be useless. But spacetime affects more than just GPS. Consider gold. The metal gold has a distinctive yellow color. It's the only metal that looks yellow. Silver is silvery white. Copper is reddish. Iron is gray. But gold is yellow. Why? The answer involves relativity. Gold atoms have 79 protons in the nucleus, creating a strong electric field. The innermost electrons are moving very fast in this strong field, fast enough that relativistic effects become important. According to special relativity, as electrons move faster, their mass effectively increases. This changes the spacing between energy levels in the atom. For gold, this relativistic effect shifts the energy levels enough that gold absorbs blue light instead of ultraviolet. When white light hits gold, the blue frequencies are absorbed, and the remaining light that's reflected is yellow. The color of gold is a relativistic effect. Without special relativity, gold would look silvery, like most other metals. The same thing happens with mercury. Mercury is the only metal that's liquid at room temperature. Why again relativity? Mercury atoms have 80 protons, and the innermost electrons are moving so fast that relativistic effects make the bonds between mercury atoms weaker than they would otherwise be. The atoms don't stick together as strongly, so mercury melts at a much lower temperature than you'd expect. Even fiber optic networks that carry internet data need to account for relativistic effects. For long-distance fiber optic communication, especially for things like financial transactions where microseconds matter, engineers have to account for relativistic effects. Cables at different altitudes experience slightly different gravitational time dilation. Every time you open Google Maps, you're trusting that space-time is curved. Every time you wear a gold ring, you're seeing a relativistic effect. Every time you use a mercury thermometer, relativity is at work. Space-time isn't an abstract concept. It affects your life in concrete, practical ways every single day. But there was a problem. Einstein's equations were beautiful, but they were also incredibly difficult to work with. They're a set of 10 interrelated equations involving tensors, which are mathematical objects that describe how space-time curves in response to mass and energy. Most physicists in the 1920s and 30s couldn't solve these equations, except in very simple cases. It's like having a brilliant recipe for the perfect meal, but it's so complicated that only 10 people on the planet can actually cook it. The recipe works, the meal is delicious, but most people can't follow the instructions. And the simplest solution to Einstein's equations led to a discovery so disturbing that Einstein himself refused to believe it was real. 1916, the Russian front, World War I. Karl Schwarzschild was a German physicist serving in the German army. Despite being in the middle of a war dealing with the harsh conditions of the Eastern Front in 1916, he found time to work on Einstein's equations. He solved them for the simplest possible case: a perfectly spherical, non-rotating mass sitting alone in empty space. The solution worked. It described how space-time curves around a star or planet. But Schwarzschild noticed something strange in the mathematics. At a certain distance from the center of the mass, the equations seemed to break. They gave infinite values. They stopped making sense. This distance became known as the Schwarzschild radius. For the Sun, the Schwarzschild radius is about 3 kilometers. For Earth, it's about 9 millimeters. These numbers seemed meaningless at the time. The Sun is much larger than 3 kilometers across. It has a radius of about 700,000 kilometers. Earth is much larger than 9 millimeters. It has a radius of about 370 kilometers. The strange behavior in the equations only appeared deep inside the physical mass, where the vacuum solution didn't really apply anyway. You can't use the vacuum solution for space-time inside a ball of matter, so most physicists ignored it. It was just a mathematical quirk, an artifact of the idealized spherical solution. Nothing to worry about. Schwarzschild himself died just a few months after publishing his solution. He contracted an autoimmune disease while serving on the Eastern Front and died in May 1916 at the age of 42. He never knew how important his solution would become. But here's what the Schwarzschild radius actually means. If you somehow compressed a mass smaller than its Schwarzschild radius, space-time would curve so strongly that nothing could escape, not even light. The object would become what we now call a black hole, and at the very center, all the mass would collapse to an infinitely small point, a singularity, a place where density becomes infinite, where the curvature of space-time becomes infinite, where the laws of physics break down completely. Einstein hated this idea. He thought it was absurd. He believed it revealed a limitation of the theory, not a prediction about reality. He believed that matter would resist being compressed that much. There would be some force, some pressure, some quantum effect that would prevent collapse beyond the Schwarzschild radius. The singularity was a mathematical artifact, not a real physical possibility. It was like dividing by zero in an equation. You get infinity, but that doesn't mean infinity exists in nature. It means you've pushed the equation beyond its domain of validity. Most physicists agreed with Einstein. The idea of a star collapsing so completely that it disappeared from the universe seemed ridiculous. Stars are held up by pressure. Hot gas pushes outward. This pressure balances gravity's inward pull. When a star runs out of fuel, it cools down, pressure drops, and gravity takes over. But surely there would be some force that would stop the collapse. Maybe the pressure of electrons pushing against each other, a quantum effect called degeneracy pressure. This is what holds up white dwarf stars. Or maybe the pressure from neutrons, which holds up neutron stars. Something would stop the collapse. It had to. But in 1939, J. Robert Oppenheimer, who would later lead the Manhattan Project, and his student Hartland Snyder published a paper that changed everything. They modeled a massive star running out of fuel, no longer able to support itself against its own gravity. They showed mathematically that there was nothing that could stop the collapse. No pressure, no force was strong enough to halt it once it started, the star would shrink past its Schwarzschild radius and keep shrinking until it became a singularity, a point of infinite density where Einstein's equations themselves broke down. It wasn't just true for idealized models. Even with realistic equations describing how matter behaves under extreme pressure, massive enough stars would still collapse completely. There's a mass limit beyond which no known force can prevent collapse to a black hole. In 1965, Roger Penrose proved a remarkable theorem. He showed that once a star collapses past a certain point, the formation of a singularity is mathematically unavoidable. It's not a matter of the star being perfectly spherical or having special properties. Any collapsing star of sufficient mass would form a singularity. The laws of physics, as described by general relativity, literally forced it to happen. In 1967, John Wheeler coined the term we use today, black hole. Before that, physicists had called them collapsed stars or frozen stars. But Wheeler's term captured something essential about them. They're holes in space-time regions where space-time itself has been torn apart. Stephen Hawking extended this work further. In the late 1960s and early 1970s, working with Penrose and others, he proved that singularities are generic features of general relativity. They don't just appear in black holes. The Big Bang itself, the beginning of the universe, was a singularity, a point of infinite density and infinite curvature where time itself began. Space-time can be bent so much that it breaks. That's what a singularity is, a place where space-time is compressed infinitely, where energy density becomes infinite, where physics collapses. This was deeply troubling. General relativity had been incredibly successful at describing gravity space-time and the motion of objects from planets to galaxies. It predicted gravitational waves. It explained GPS. It explained how light bends around the sun. Every prediction had been confirmed. But the theory itself predicted places where it broke down, places where the equations gave infinite answers and stopped making sense. Singularities were like signs posted in the mathematics saying, beyond this point, physics doesn't work. Einstein died in 1955, never accepting that black holes were real. He thought they showed that general relativity must be incomplete, that something was missing from the theory. But he couldn't find a flaw in the mathematics. The equations were correct. General relativity really did predict these objects. The universe didn't care what Einstein believed. Black holes exist. We've found them, we've measured them, and now we've even photographed them. 2019, the Event Horizon Telescope, 8 radio telescopes spread across the entire planet, from Hawaii to Antarctica, from Spain to Chile, all pointed at the same target at the same time, combined using a technique called very long baseline interferometry. They created a telescope effectively the size of Earth. The resolution this provides is extraordinary. With this setup, you could read a newspaper in New York from a cafe in Paris. You could see an orange sitting on the surface of the moon. But the team wasn't looking at oranges or newspapers. They were looking at something far more extreme. The telescopes recorded radio waves at a wavelength of 1.3 millimeters, a frequency where the gas around black holes glows brightly. They collected petabytes of data, so much data that it couldn't be sent over the internet. Hard drives had to be physically shipped by airplane to a central facility for processing. The target was 87 Star, a supermassive black hole at the center of the galaxy Messier 87, about 55 million light-years away. This black hole weighs 6.5 billion times the mass of the Sun. The result was an image that made headlines around the world. A ring of glowing orange light surrounding absolute darkness. The dark region in the center, the shadow, is the event horizon, the point of no return, the boundary where nothing can escape. The diameter of that shadow is about 40 billion kilometers. That's about 3 times the size of Pluto's orbit around the Sun. The ring of light is gas orbiting the black hole, at speeds approaching the speed of light, heated to billions of degrees by friction and magnetic fields. It glows in X-rays, visible light, and radio waves. But here's what's remarkable about this image. The light from that gas has been bent by space-time, severely bent. Some photons orbit the black hole multiple times before escaping. Some are bent just enough to reach our telescopes. The ring appears brighter on one side because the gas is rotating. On one side it's moving toward us, and relativistic effects make it appear brighter. On the other side, it's moving away and appears dimmer. What you're seeing is not the black hole itself. The black hole is the dark circle in the center, the region from which no light escapes. What you're seeing is the effect of the black hole on space-time around it. Light is being twisted, curved, focused by curved space-time. The image is a direct photograph of Einstein's predictions made visible. In May 2022, the collaboration released an image of a second black hole, this one at the center of our own galaxy, Sagittarius A star. It's about 4 million times the mass of the Sun, much smaller than M87 star, but it's much closer, only about 27,000 light-years away, instead of 55 million. Again, the image shows a ring of light around darkness. You're looking at real photographs of space-time bent to its breaking point, not CGI, not artists' interpretations, real photons that traveled for millions or tens of thousands of years to reach Earth. But we have even more direct evidence of space-time in action. Remember September 14th, 2015 LIGO detected gravitational waves from 2 black holes colliding. Each black hole was about 30 times the mass of the Sun. In the final second, before they merged, they were orbiting each other hundreds of times per second, moving at significant fractions of the speed of light. When they collided, the merger released the energy equivalent of 3 solar masses in less than 1 second. That's the equivalent of annihilating 3 suns and converting all their mass directly to energy. That energy radiated outward as ripples in space-time, traveling at the speed of light. After 1.3 billion years, those ripples reached Earth. They made space-time vibrate by about 10 to the minus 18 meters, 1/10,000th the width of a proton, and LIGO detected it. Since 2015, LIGO and its sister observatories have detected dozens of collisions, black holes merging, neutron stars merging. Each detection is direct evidence that space-time is real, that it can vibrate like a drumhead. In August 2017, something extraordinary happened. LIGO and Virgo detected gravitational waves from 2 neutron stars merging about 130 million light-years away. This event was special because neutron star mergers also produce light. Unlike black holes, which are dark, neutron stars are made of normal matter, and they glow. Within seconds of the gravitational wave detection, LIGO sent out alerts to astronomers around the world. Telescopes swung into action, searching the region of sky where the signal came from. Within hours, they found it, a new bright source in a galaxy called NGC 4993. Over the following days and weeks, dozens of telescopes observed the kilonova at different wavelengths, from gamma rays to radio waves. It was the first time humanity had observed a cosmic event with both gravitational waves and light, the dawn of multi-messenger astronomy, and the observations confirmed something physicists had long suspected. Heavy elements like gold, platinum, and uranium are created in neutron star mergers. The collision creates conditions so extreme that atomic nuclei are smashed together and rebuilt into heavy elements. The kilonova ejected about 1/100th of a solar mass of material, much of it gold and platinum. All the gold on Earth, every gold ring, every gold coin, every gold bar in bank vaults, was created in neutron star mergers billions of years ago, before the solar system formed. The gold was scattered into space, mixed with gas and dust, and eventually incorporated into the disk of material that formed the sun and planets. When you wear a gold ring, you're wearing atoms that were forged when space-time shook violently from a cosmic collision. The ring on your finger is proof that space-time can be torn apart and stitched back together. The evidence is overwhelming. Space-time exists. We can measure it vibrating. We can photograph it bending. We use it every single day. But here's the paradox. The more we study it, the less we understand what it actually is. General relativity explains perfectly how space-time behaves, how it curves in response to mass, how objects move through it, how waves propagate through it. The theory has never failed a test, but general relativity doesn't explain what space-time is. It describes its behavior without explaining its nature. It's like having a detailed instruction manual for an iPhone. You know how to use every feature. You can predict exactly what will happen when you press each button, but you have no idea what's inside the phone. Is it chips and circuits, gears and springs, or magic? We have three big unanswered questions, three mysteries that sit at the frontier of human knowledge. First, what is space-time made of? At the smallest scales, at the Planck scale of 10 to the minus 35 meters. What is this fabric actually composed of? Second, what happened at the Big Bang, when space-time itself began from a singularity? What actually occurred? Third, do black holes destroy information? When something falls into a black hole, is the information about it lost forever? These three questions are where modern physics hits its limits, where our best theories stop working, where the map runs out and we're left staring into the unknown. And the first question, the question of what space-time is made of, takes us down the rabbit hole of quantum mechanics. Here's the fundamental problem. Einstein said space-time is smooth and continuous. You can zoom in on any point in space, and there's always more space at smaller scales. You can divide time into smaller and smaller intervals, and there's always more time. Space and time are continuous, infinitely divisible, like a perfectly smooth line of real numbers. But quantum mechanics says something completely different. Almost everything in nature is discrete, quantized, coming in chunks rather than being continuous. Energy comes in chunks called quanta. Light comes in chunks called photons. Even the spin of an electron comes in discrete values. You can't have half a photon. You can't have an electron spinning at an arbitrary angle. The quantum world is fundamentally grainy, not smooth. This suggests something profound. If everything else in nature is quantized, then space and time might also be quantized at very small scales. There might be a smallest possible length, a quantum of space. There might be a smallest possible duration, a quantum of time. Below these scales, it doesn't make sense to talk about smaller distances or shorter times. This scale is called the Planck length. It's about 10 to the minus 35 meters. That's incomprehensibly small. A proton is about 10 to the minus 15 meters across. The Planck length is 20 orders of magnitude smaller than a proton. Let me give you a sense of scale. If you could scale a proton up to the size of the observable universe, about 10 to the 26 meters across the Planck length would be about the size of a tree. That's the ratio we're talking about. At this scale, quantum effects on spacetime itself should become important. The smooth fabric of spacetime Einstein described should break down into something else, something grainy, something chaotic. Physicists call this quantum foam. It's the idea that if you could zoom in, far enough spacetime would look turbulent, bubbling with quantum fluctuations, constantly forming and dissolving tiny structures. Space and time would oscillate wildly unstably. The smooth fabric would reveal itself to be made of something discrete, something choppy, something that looks nothing like the serene continuum we experience at large scales. But here's the problem. We have no direct way to probe these scales. To explore physics at the Planck length, you'd need to reach the Planck energy. That's about 10 to the 19 giga-electron volts. The Large Hadron Collider, the most powerful particle accelerator ever built, reaches energies of about 10 to the 4 giga-electron volts. That's 14,000 giga-electron volts. To probe the Planck scale, you'd need an accelerator about 10 to the 15 times more powerful than the LHC. That's 1,000 trillion times more powerful. Building such a machine is far beyond our technological capabilities. It might be beyond the capabilities of any civilization bound by the laws of physics as we understand them. It's like trying to see the smallest pixel on the screen of the universe. But your microscope isn't powerful enough. It will never be powerful enough. The pixel is too small. The energy required to see it is too high. The universe itself seems to have placed a barrier between us and the fundamental nature of spacetime. So we're stuck. We have to use mathematics theory and indirect reasoning. We can't run direct experiments. We can't build machines powerful enough to test our ideas. And that means we can't definitively choose which theory is correct. There are three main theories competing to explain what spacetime is made of at the Planck scale. Loop quantum gravity says spacetime is woven from tiny loops. String theory says spacetime emerges from vibrating strings in 10 or 11 dimensions. And emergent spacetime says spacetime isn't fundamental at all, but arises from quantum entanglement. All three theories are beautiful. All three have elegant mathematics. All three are logically consistent, but none of them can go on a date with reality to prove they're right. They're stuck in the theoretical world, unable to make contact with experiment. It's like having three incredibly attractive, intelligent, charming potential partners. On paper, they're all perfect. but you can never actually meet them in person to see if there's real chemistry. You're left looking at their profiles, admiring their qualities, but never knowing which one is actually right for you. And we begin with the simplest idea. What if space-time is made of loops? The idea behind loop quantum gravity is straightforward. Take Einstein's equations and quantize them directly. Don't add anything extra. Don't invoke extra dimensions or new particles. Just apply the rules of quantum mechanics to general relativity and see what happens. What you get is remarkable. Space-time is woven from tiny loops, each about a Planck length in size. These loops connect to form a network like a fabric made of thread. The geometry of space-time emerges from how these loops are arranged and connected. In this picture, area and volume are quantized. You can't have an arbitrary area or volume. They come in discrete units, multiples of the Planck length squared for area, or Planck length cubed for volume. Space-time has a minimum possible volume. You can't divide it any smaller. Think of it like a digital photograph. From far away, the image looks smooth and continuous. But zoom in close enough, and you see individual pixels. The smoothness is an illusion that emerges when you step back. Loop quantum gravity says space-time is like that, smooth at large scales, but fundamentally discrete at small scales. This solves a major problem. Remember, singularities, those points of infinite density where general relativity breaks down. In loop quantum, gravity singularities might not actually exist. Instead of collapsing to an infinitely small point, matter would collapse to a minimum volume set by quantum effects. The singularity would be replaced by a quantum bounce. At the center of a black hole, instead of a singularity, there would be a tiny quantum structure. At the Big Bang, instead of starting from a point of infinite density, the universe would bounce from a previous contracting phase. The quantum nature of space-time would prevent the complete collapse. It would be like trying to compress water. You can push it hard, but eventually the molecules resist. They can't be squeezed infinitely close. The appeal of loop quantum gravity is that it stays true to Einstein's spirit. Space-time remains fundamental. It's not emergent from something else. It's just quantized, made discrete, at small scales. And the theory eliminates the infinities that plagued general relativity. No more singularities. No more places where physics breaks down. From a distance you see smooth space-time. Zoom in to the Planck scale, and you see the threads, the loops, the discrete structure. But loop quantum gravity has serious problems. The mathematics is extremely complex. The equations are difficult to solve, even more difficult than Einstein's equations. And it's hard to extract predictions that can be tested. The theory makes statements about what happens at the Planck scale, but how do you verify them when you can't build experiments that reach those energies more seriously? Loop quantum gravity hasn't been successfully unified with the other forces of nature. It's a quantum theory of gravity, but it doesn't naturally incorporate electromagnetism, the weak nuclear force, or the strong nuclear force. Those forces are described by quantum field theory, the framework that describes how particles interact. And loop quantum gravity hasn't been connected to quantum field theory in a satisfying way. It's like having a recipe for baking a delicious cake, but you don't have recipes for the frosting, the filling, or the decorations. The cake by itself might be good, but it's not enough for the full party. You need everything working together. Some physicists believe loop quantum gravity correctly describes space-time itself, but it's incomplete. It's missing the supporting cast. It has the main character, space-time, but not the other characters, the particles and forces that live in space-time. Loop quantum gravity is like having a brilliant movie script with only one actor. You need the full ensemble cast to make the film work. Right now, the lead actor is on stage alone, delivering a monologue. It's impressive, but it's not the complete story. And that leads us to a far more ambitious theory, one that attempts to unify everything, not just gravity, but all particles and all forces into a single framework built from vibrating strings. The core idea of string theory is radical. Fundamental particles aren't points. They're tiny vibrating strings about a Planck length in size. Different vibrations of these strings correspond to different particles. One vibration pattern creates an electron. A different vibration creates a quark. Another vibration creates a photon. And one particular vibration corresponds to the graviton, the hypothetical quantum particle that would carry the gravitational force. Think of it like a guitar string. Pluck it one way, you get one note. Pluck it differently, you get another note. The string is the same, only the vibration changes. In string theory, the universe is like a cosmic symphony. Every particle is a note played on these fundamental strings. But here's where it gets strange. In string theory, space-time emerges from the interactions of these strings. The strings don't exist in our familiar four-dimensional space-time. They exist in a higher dimensional space, usually 10 or 11 dimensions, not 4. Where are these extra dimensions? They're curled up so small, we don't notice them. Compactified at scales near the Planck length. Imagine a water hose. From far away, it looks like a one-dimensional line, but zoom in close, and you see it has a two-dimensional surface wrapped around in a circle. The extra dimension is hidden at small scales. String theory says our universe is like that. We experience 3 dimensions of space and 1 of time, but there are 6 or 7 extra dimensions, curled up so tiny we can't detect them. The geometry of spacetime, the curvature we experience as gravity, emerges from how the strings move and interact in this higher dimensional space. Spacetime isn't fundamental in string theory. It's a consequence of string dynamics. String theory has enormous advantages. The mathematics is consistent. Unlike other attempts to quantize gravity that run into contradictions, string theory is mathematically coherent. It naturally includes gravity. The graviton emerges automatically as one of the string vibrations. You don't have to force it in. It's already there. And it unifies all the forces. Electromagnetism, the weak nuclear force, the strong nuclear force, and gravity all emerge from the same framework. They're all just different vibrations of strings. It's the ultimate unification. Everything from one object, one idea. The mathematics is also deeply beautiful. It connects to advanced pure mathematics in surprising ways. Mathematicians have discovered new theorems by studying string theory. The theory has a rich mathematical structure that goes far beyond physics. The history of string theory is fascinating. It emerged in the 1970s, initially as an attempt to describe the strong nuclear force. That didn't work out. The theory failed to explain the strong force. But physicists realized the theory naturally contained a description of gravity. So it was repurposed. Instead of explaining the strong force, It became a candidate for the theory of everything. In the 1980s and 90s, string theory developed rapidly. But there was a puzzle. Physicists discovered there were 5 different versions of string theory, all mathematically consistent, but apparently different. This was troubling. If string theory was the fundamental theory of nature, there should only be one version. Why 5? Then in 1995, Edward Witten proposed a solution. He suggested that all 5 versions were actually different limits of a single, more fundamental theory, which he called M theory. M theory works in 11 dimensions, 10 of space, and 1 of time. The 5 string theories are different ways of looking at this same underlying theory. It was a major unification, suggesting that string theory might truly be unique. String theory makes concrete predictions. It predicts supersymmetry, a hypothetical symmetry that relates particles of different spins. For every known particle, there should be a supersymmetric partner. The electron would have a partner called the selectron. Quarks would have partners called squarks. Photons would have partners called photinos. If supersymmetry exists, it would solve several problems in particle physics. It would provide a natural candidate for dark matter. It would explain why certain parameters in the Standard Model have the values they do. The Large Hadron Collider was built partly to search for these supersymmetric particles. But here's problem number 1. We've searched for supersymmetric particles extensively at the LHC. We haven't found any. The LHC has probed energies up to about 14,000 giga-electron volts, creating collisions energetic enough that supersymmetric particles should have been produced if they exist at accessible energies. But we haven't seen them. This doesn't rule out supersymmetry completely. The particles might be heavier than we can produce. But it's disappointing. It's like throwing an elaborate birthday party, inviting your new best friends, decorating everything perfectly, baking the cake, and nobody shows up. The party looks great, but it's empty. Problem number 2 is even more serious. It's called the landscape problem. The extra dimensions in string theory can be compactified in many different ways. Each way gives you a different 4-dimensional theory with different particles and forces. Current estimates suggest there might be 10 to the 500 different versions, maybe more. Let that number sink in. 10 to the 500. That's incomprehensibly large. It's far more than the number of atoms in the observable universe, which is only about 10 to the 80. The landscape of possible string theories is 420 orders of magnitude larger than the number of atoms in existence. With 10 to the 500 possible string theories, how do we know which one describes our universe? There's no principle within string theory that selects one vacuum over another. The theory doesn't predict which universe we should live in. Some physicists have proposed a controversial solution: anthropic reasoning. Maybe all of these 10 to the 500 vacua are real. Each one describes a different universe in a vast multiverse. Our universe just happens to be one particular point in this landscape. We exist in this particular universe because the physical constants happen to allow stars, planets, and life to form. In other universes, with different constants, life might not be possible, so there's no one there to observe them. Many physicists hate this idea. It seems to give up on the goal of explaining why the laws of physics have the specific form they do. Instead, it says the laws are essentially random, different in different universes. and we live in one of the rare universes where the laws allow life. It's not a satisfying explanation. It doesn't predict anything. It turns physics into a lottery. We won the cosmic lottery by being born in a universe with the right constants. That's not explanation. That's just luck. Problem number 3 is the most fundamental. String theory makes almost no testable predictions at energies we can reach. The natural scale of string theory is the Planck energy, about 10 to the 19 giga-electron volts. The LHC reaches energies of about 10 to the 4 giga-electron volts. To probe the Planck scale directly, we'd need an accelerator 10 to the 15 times more powerful than the LHC, 1,000 trillion times more powerful. Building such a machine is far beyond our technological capabilities. It might be beyond the capabilities of any civilization. Without testable predictions, how do we know string theory is right? It's mathematically beautiful. It's logically consistent. It unifies forces in an elegant way. But beauty and elegance aren't proof of truth. String theory has produced real achievements. It's given us new mathematical tools for doing calculations in quantum field theory. It's revealed deep connections between different areas of physics and mathematics. The ADS-CFT correspondence, which we'll discuss in a moment, is one of the most important discoveries in theoretical physics in the past 30 years. But as a theory of fundamental reality, as a quantum theory of gravity that explains what space-time really is, it remains unproven. Some physicists argue that string theory has become more of a mathematical framework than a physical theory. It's beautiful mathematics, but is it about our universe? Or is it just elegant structures that happen to be logically consistent but have nothing to do with reality? String theory is like finding your perfect soulmate on paper. Attractive, intelligent, funny kind, everything matches. You're perfect for each other. Except they live in a parallel universe you can never visit. The relationship looks perfect in theory, but you can never actually be together. And now the story gets truly strange. What if space-time doesn't exist at all? Here's the most radical idea. Space-time isn't fundamental. It's an emergent phenomenon that arises from something deeper, something that doesn't look like space or time at all. Think about temperature. Temperature feels real. You can measure it. You can feel hot and cold. But temperature isn't fundamental. It emerges from the motion of molecules. If you could track every single molecule, knowing their positions and velocities perfectly, you wouldn't need the concept of temperature. Temperature is a useful description that emerges when you step back and look at the average behavior of trillions of molecules. Similarly, pressure in a gas isn't fundamental. It emerges from molecules bouncing off the walls of a container. The molecules are fundamental. Pressure is what emerges when you have lots of molecules acting together. What if space-time is like that? What if space and time emerge from something more fundamental, something that doesn't look like space or time? Let's talk about quantum entanglement. This is one of the strangest phenomena in quantum mechanics. Two particles can be entangled such that measuring one instantly affects the other, no matter how far apart they are. This isn't communication faster than light, because you can't control the outcome of your measurement, but it is a genuine correlation that exists across space without anything traveling through the space between. In 1935, Einstein and two colleagues, Boris Podolsky and Nathan Rosen wrote a paper describing this phenomenon. They called it the EPR paper. They thought entanglement showed that quantum mechanics was incomplete. They believed the correlations must be explained by some hidden information the particles carried with them. But experiments have shown the correlations are real and can't be explained by hidden information. Entanglement is a genuine feature of quantum mechanics. Also, in 1935, Einstein and Nathan Rosen wrote another paper. This one was about solutions to general relativity that contained wormholes, shortcuts through spacetime connecting distant regions. These became known as Einstein-Rosen bridges, or ER bridges, but the wormholes in their solution were unstable. They'd collapse before anything could pass through them. In recent years, physicists have wondered if there might be a connection between entanglement and wormholes. The idea is summarized by the equation ER equals EPR. ER stands for Einstein-Rosen bridges. EPR stands for Einstein-Podolsky-Rosen entanglement. The suggestion is that when two particles are entangled, they're connected by a tiny wormhole, a thread of space-time linking them. The wormhole is too small to travel through. You can't send information through it, but it maintains the quantum correlation. If this is true, it would mean something profound. Space-time itself is woven from entanglement, the connections between distant points in space. The geometry that we think of as space-time would emerge from quantum correlations between particles. If ER equals EPR, then space is an illusion, a useful way of describing something more fundamental. Distance would emerge from the pattern of entanglement. Strongly entangled particles would be close together. Weakly entangled particles would be far apart. Space emerges from information. This connects to something called the holographic principle. In the 1990s, physicists studying black holes realized something strange. Black hole entropy is proportional to the area of the event horizon, not the volume. For ordinary objects, entropy is proportional to volume. A bigger box can hold more information. But for black holes, it's the surface area that matters. This suggests that the information in a volume of space can be encoded on the boundary of that volume. The three-dimensional universe might be a hologram, with all its information encoded on a two-dimensional surface. This is the holographic principle. The most concrete realization of this idea is the ADS-CFT correspondence. ADS stands for anti-de Sitter space, a particular geometry used in string theory. CFT stands for conformal field theory, a type of quantum field theory. The correspondence says that a theory of gravity in a higher dimensional ADS space is mathematically equivalent to a quantum field theory without gravity on the boundary of that space. This is one of the most important discoveries in theoretical physics in the past 30 years. It proves, at least in this specific mathematical model, that gravity and space-time can emerge from a quantum theory that doesn't contain space-time as a fundamental ingredient. It's like discovering that the solid table you're touching is actually 99.99% empty space. The solidity is an illusion created by electromagnetic forces between atoms. You think you're touching something solid, but you're actually feeling forces between clouds of electrons. The table isn't fundamentally solid. Solidity emerges at large scales. If space-time is emergent, then at the deepest level, There is no space. There is no time. There's only quantum information, quantum bits, and the correlations between them. Space-time crystallizes from the pattern of these correlations at large scales. Many leading physicists believe this is the right direction. John Wheeler, one of the great physicists of the 20th century, coined the phrase, "it from bit." Physical reality emerges from information. Space-time might be no more fundamental than temperature. It's a useful description that emerges when you zoom out, but is not the deepest level of reality. The problem is that we don't yet have a complete theory. ER equals EPR is a conjecture, not a proven theorem. The holographic principle works in special models, particularly in ADAS space, but it hasn't been successfully applied to our actual universe, which appears to be de Sitter space, not ADS. We're still missing pieces. But if this is true, the philosophical implications are staggering. The distance between you and the moon would be an illusion. Now wouldn't exist as an absolute concept. Past, present, and future wouldn't be truly separate. Everything would just be different arrangements of quantum information. Every time you measure a distance with a ruler, you're actually measuring the degree of entanglement between particles. The meter isn't fundamental. The entanglement is. It's like discovering you've been living inside a simulation your whole life. Except instead of computer code, the simulation is made of quantum bits. Everything you think is real. The space around you, the time flowing forward, is just a convenient fiction that emerges from quantum correlations. If this is true, it's the most radical view of reality in the history of science. More radical than relativity. More radical than quantum mechanics. It would mean that our most basic intuitions about existence are wrong. Space and time aren't the stage on which reality plays out. They're part of the play itself, emerging from something deeper. Let's summarize. We have three theories competing to explain what space-time is made of. Loop quantum gravity says space-time is woven from quantum loops. It's discrete, not continuous. There's a minimum volume. Singularities are replaced by quantum structures. String theory says space-time emerges from vibrating strings in 10 or 11 dimensions. The extra dimensions are curled up at the Planck scale. Geometry emerges from string dynamics in higher dimensional space. Emergent space-time says space-time isn't fundamental at all. It emerges from quantum entanglement. Space is an illusion, arising from correlations between quantum bits. All three theories have beautiful mathematics. All three are logically consistent. All three make sense within their own frameworks, but they make different predictions about the nature of reality at the Planck scale. And here's the fundamental problem. We can't test them directly. To probe the Planck scale, you'd need energies of about 10 to the 19 giga-electron-volts. The LHC reaches 10 to the 4 giga-electron-volts. The gap is 10 to the 15, 1,000 trillion. If the LHC is a spoon, you'd need a weapon as powerful as the sun to reach the Planck scale. We're stuck. We can't build an accelerator powerful enough. The energy required violates every practical limit. It might violate fundamental physical limits. We can't see the Planck scale with any microscope we could ever build. So we're left with mathematics and indirect reasoning. We search for indirect evidence. We examine the cosmic microwave background, looking for traces of quantum gravity effects. From the Big Bang, we search for violations of Lorentz invariance tiny deviations in the constancy of the speed of light at high energies. We analyze cosmic rays looking for anomalies. We study theoretical models of Hawking radiation from tiny black holes, if they exist. So far, we've found nothing. No smoking gun. No clear signal pointing to one theory over the others. It's like being a detective with 3 perfect suspects. Each has means motive and opportunity, but all 3 have airtight alibis you can't break. And here's the truly frightening possibility. Maybe physics at the Planck scale doesn't affect anything we can measure at large scales. Maybe there's decoupling. The physics of the very small might be completely separated from the physics of the large. If that's true, we might never know which theory is correct through experiment. We might have reached the final limit of experimental science. Some physicists worry about this, not because of limited intelligence or technology, but because of fundamental limits imposed by the universe itself. The Planck scale might be forever beyond our reach. Not practically beyond our reach, but fundamentally absolutely beyond our reach. But there's hope. History is filled with problems that seemed impossible to solve until someone had a new idea. Quantum mechanics emerged from the crisis of classical physics at the beginning of the 20th century. General relativity solved contradictions about gravity that had persisted for 300 years. Breakthroughs often come from unexpected directions. The breakthrough might come from new mathematics that hasn't been invented yet, or from unexpected connections between current theories. Maybe loop quantum gravity and string theory are different descriptions of the same thing, or from new astronomical observations. Primordial black holes, if they exist, and we find them. Quantum gravity effects in the cosmic microwave background, or from a completely new idea that lies outside all 3 current frameworks. Maybe the answer is something we're currently ignoring, like searching everywhere for your keys, and then realizing they've been in your pocket the whole time. The solution might be obvious in retrospect. It always is. This is question 1 of 3. What is spacetime made of? We don't know. And it leads directly to question 2. Because if we don't know what spacetime is made of, how can we understand how it began? If we can't describe the fabric at its most fundamental level, how can we describe its creation? We need to go back 13.8 billion years, to the Big Bang. The universe is expanding. This was discovered by Edwin Hubble in 1929. He observed that the farther away a galaxy is, the faster it's moving away from us. The light from distant galaxies is redshifted. The wavelengths are stretched because space itself is expanding while the photons are traveling toward us. If the universe is expanding now, it must have been smaller in the past. Run the clock backward. If everything is moving apart now, then in the past, everything was closer together. Keep going back. The universe gets smaller, denser, hotter. Eventually, about 13.8 billion years ago, everything was compressed into an infinitely small, infinitely dense point. A singularity. This is the Big Bang singularity. Infinite density, infinite temperature, infinite curvature of spacetime. Einstein's equations give you infinity as the answer, and infinity in physics means the math has stopped working. It means we don't actually know what happened. The equations break down. They can't be trusted. We have overwhelming evidence for the Big Bang in a general sense. 2 main pieces of evidence stand out. First, the universe is expanding. Hubble measured that. Second, the cosmic microwave background radiation. This was discovered in 1964, and the story of its discovery is fascinating. Arno Penzias and Robert Wilson were working at Bell Labs in New Jersey. They were using a large horn antenna to measure radio signals from the Milky Way, but they kept detecting an annoying background noise that wouldn't go away. No matter which direction they pointed the antenna, no matter what time of day or night, the noise was always there. Same intensity, everywhere. At first, they thought it might be interference from New York City, but the signal was the same from all directions. Cities don't radiate uniformly in all directions. They thought it might be heat from the ground or the atmosphere, but the signal had the wrong spectrum for thermal emission from Earth. Then they thought it might be from bird droppings in the antenna. They actually cleaned the antenna, thoroughly removing what they politely called white dielectric material. Pigeon droppings. They cleaned out the pigeon poop. The signal persisted. Finally, they learned that theoretical physicists at Princeton University, just a few kilometers away, had predicted exactly such a signal. If the universe had started in a hot, dense state and expanded and cooled, there should be leftover radiation from that early hot phase. The radiation would have been stretched by the expansion of the universe from high-energy gamma rays down to microwave frequencies, and it should be coming from all directions uniformly, because the early universe was nearly uniform everywhere. Penzias and Wilson had accidentally discovered proof of the Big Bang. The cosmic microwave background is light left over from when the universe was only about 380,000 years old. Before that time, the universe was so hot that atoms couldn't form. The temperature was over 3,000 Kelvin. At that temperature, electrons have enough energy to escape from atomic nuclei. Electrons and protons existed separately as a hot plasma. In this plasma state, light couldn't travel very far. Photons would constantly scatter off the free electrons, bouncing from electron to electron like a ball in a pinball machine. The universe was opaque. You couldn't see through it because light was constantly being absorbed and re-emitted by the plasma. But as the universe expanded and cooled eventually, the temperature dropped below 3,000 Kelvin. At this point, electrons and protons could combine to form neutral hydrogen atoms. This happened rather suddenly across the entire universe, a transition called recombination. Suddenly, light could travel freely. The universe became transparent. Photons could stream through space without being scattered. Those photons have been traveling ever since. They've been stretched by the expansion of the universe from visible light with wavelengths of about 500 nanometers to microwave radiation with wavelengths of about 2 millimeters. The redshift factor is about 1/100. The universe has expanded by a factor of 1/100 parts. Since recombination, we can detect this radiation today coming from every direction in the sky. It's a nearly uniform glow with a temperature of about 2.725 Kelvin, just a few degrees above absolute zero. But it's not perfectly uniform. There are tiny variations, slight differences in temperature from one direction to another. Some regions are slightly warmer, about 2.7255 Kelvin. Some are slightly cooler, about 2.7245 Kelvin. The variations are only about 1 part in 100,000, incredibly small, but they're real and they're incredibly important. These variations are the seeds of structure in the universe. Regions that were slightly denser had slightly higher temperatures. These regions had slightly stronger gravity. Over billions of years, matter was pulled into these slightly denser regions. The dense regions became denser. The less dense regions became emptier. Over time, the tiny variations grew into the galaxies, galaxy clusters, and superclusters we see today. Every atom in your body exists because of tiny quantum fluctuations in the early universe that left their imprint on the cosmic microwave background. You are made of stardust, yes, but before that, you're made of quantum fluctuations from the first fraction of a second of cosmic history. We've mapped these temperature variations with incredible precision using satellites. The COBE satellite in the early 1990s made the first detections. The WMAP satellite from 2001 to 2010 mapped the sky in much higher resolution. The Planck satellite from 2009 to 2013 produced the most detailed map yet measuring temperature variations across the entire sky with a resolution of about 5 arc minutes. From these maps, we can determine fundamental properties of the universe. The age currently 13.8 billion years. The composition about 5%, normal matter, like atoms about 27%, dark matter, which we can't see directly, but which has gravitational effects, and about 68% dark energy, causing the expansion to accelerate. The geometry of space, which appears to be flat, meaning parallel lines stay parallel forever, rather than converging or diverging. The rate of expansion, the Hubble constant. All of this from studying tiny temperature variations in ancient light. The cosmic microwave background matches the predictions of Big Bang cosmology with better than 99% precision. It's one of the most successful theories in the history of science. But there's a problem. When we try to understand the very beginning, the first moments, we run into a wall. The Planck time about 10 to the minus 43 seconds after the Big Bang. Below this time, scale quantum effects on spacetime should become important. General relativity can't be trusted. We need a quantum theory of gravity, and we don't have one. It's like having high-definition video of an embryo developing over 9 months, but the first moment of conception is missing. The file is corrupted. The crucial instant is hidden behind a wall of ignorance. Einstein died in 1955, believing there was something wrong with the Big Bang. He thought the universe should be eternal, unchanging. He actually added a term to his equations, the cosmological constant, to keep the universe static. When Hubble discovered the expansion, Einstein called it the biggest blunder of his career. But the evidence is overwhelming. The universe had a beginning, and here's something important to understand. The Big Bang wasn't an explosion in space. It was the expansion of space itself. Space didn't exist before the Big Bang, and then explode. Space itself came into being and started expanding. There's no center. Every point is expanding away from every other point. If you ask where the Big Bang happened, the answer is everywhere. It happened at every point in space simultaneously because all of the space was compressed to a point. Asking where the Big Bang happened is like asking what's north of the North Pole. The question doesn't make sense. There is no north of the North Pole. There's no location for the Big Bang because location is defined by space, and space itself emerged from the Big Bang. And there's a theory that tries to patch this gap. In the early 1980s, Alan Guth and others proposed an idea called cosmic inflation. The idea is that in the very first fraction of a second The universe underwent a period of exponentially rapid expansion between about 10 to the minus 36 seconds and 10 to the minus 32 seconds after the Big Bang. Space expanded by at least a factor of 10 to the 26, a region smaller than a proton inflated to the size of a grapefruit or larger. This solves three major problems. First, the horizon problem. Why does the universe look so uniform in all directions? Regions of space that are now billions of light years apart have the same temperature to incredible precision, but they're so far apart that light hasn't had enough time to travel between them since the Big Bang. They've never been in contact. They've never been able to communicate. So how did they come to the same temperature? Inflation solves this. Before inflation, these regions were close together, close enough to interact and come to the same temperature. Then inflation stretched them apart. The uniformity was established before. Inflation then preserved as space expanded. Second, the flatness problem. Why is space so flat? Space could be curved, like the surface of a sphere, positively curved, or it could be curved like a saddle, negatively curved. But measurements show that space is almost perfectly flat. Parallel lines stay parallel. This requires incredible fine-tuning of the initial conditions. Why is the universe so flat? Inflation solves this. Any initial curvature would have been stretched out by the rapid expansion, just like the surface of a balloon looks flatter the more you inflate it. Blow up a balloon to the size of the observable universe, and any small patch would look perfectly flat. Third, the structure problem. Where did galaxies come from? Why isn't the universe perfectly smooth? Quantum fluctuations during inflation would have been stretched to cosmic scales. These tiny fluctuations in density created the variations we see in the cosmic microwave background. Over billions of years, these small variations grew into galaxies and clusters of galaxies. The evidence supports inflation. The patterns in the cosmic microwave background match the predictions of inflation. The power spectrum of the fluctuations, the distribution of variations at different scales, fits the theory remarkably well. But inflation doesn't solve the singularity problem. It just pushes it back. Inflation requires very specific initial conditions. You need a particular kind of energy field, called a scalar field with specific properties, to drive the expansion. Where did these conditions come from? Inflation doesn't answer that. And if you trace inflation backward in time, you still reach a singularity. There are alternative ideas. One is the Big Bounce. Maybe the universe didn't begin with a singularity. Maybe it was contracting before the Big Bang reached a minimum size, and then bounced, transitioning from contraction to expansion. Loop quantum gravity suggests this might happen. Quantum effects would stop the collapse before it reached a singularity, creating a quantum bounce. But the mathematics isn't fully worked out yet. Another idea is quantum tunneling from nothing. Maybe the universe emerged from nothing through a quantum process. In quantum mechanics, nothing isn't really empty. There are quantum fluctuations, virtual particles popping in and out of existence. Maybe the universe is a giant quantum fluctuation. But what does nothing mean when there's no space-time? How can something tunnel from nothing if there's no time for the tunneling to occur? A third idea is eternal inflation. Maybe inflation never completely stops. Different regions of space stop inflating at different times, creating pocket universes. Our observable universe would be just one pocket in an eternally inflating multiverse. But the other pockets are forever beyond our cosmic horizon. We can never observe them. It's speculation without possibility of verification. It's like knowing you were born in a hospital delivery room, but having no idea how the hospital itself was constructed. You know the immediate circumstances of your birth, but the deeper origin remains mysterious. All of these ideas are speculative. None has direct experimental evidence. The question of what happened at the Big Bang remains open. We know the universe had a beginning. We know it was incredibly hot and dense. We know its age is 13.8 billion years. But the very first moment, the instant t equals 0, is hidden behind a wall of ignorance. We need quantum gravity to go further, and we don't have it. This is question 2, and it connects to question 3 through singularities. The Big Bang and black holes are like two siblings. One creates space-time, one destroys it. Both involve singularities. Both push our theories to their breaking point. And speaking of destruction, do black holes destroy information? In quantum mechanics, information is sacred. The Schrödinger equation is deterministic. If you know the quantum state of a system, at one time you can calculate its state at any other time, past or future. Information is never destroyed. This principle is called unitarity. Information might get scrambled. It might get spread out among many particles in incredibly complex ways. It might be hidden so thoroughly that extracting it becomes practically impossible. But it's always there in principle. The processes of quantum mechanics are reversible. If you know the final state perfectly and run the equations backward, you can recover the initial state. Information is conserved. But black holes seem to violate this. Imagine you throw a book into a black hole. The book contains information, the words on each page, the precise positions of all the atoms that make up the paper and ink, the quantum state of every particle. All of that is information. The book crosses the event horizon and falls toward the singularity. From the outside, the black hole has gained a tiny bit of mass, equal to the mass of the book, but you can't tell what fell in. The black hole doesn't carry any trace of the words on the pages. John Wheeler summarized this by saying, "Black holes have no hair. They have no features that distinguish what went into them. A book, a rock, a star. The black hole looks the same regardless. It's characterized only by its mass, its spin, and its electric charge. Nothing else. If black holes were eternal, you might say the information is still there, locked inside the black hole forever, inaccessible, but not destroyed." But in 1974, Stephen Hawking discovered something that changed everything. Black holes aren't completely black. They emit radiation. Hawking combined general relativity with quantum mechanics in a very specific way. Here's how it works. Quantum mechanics says that empty space isn't really empty. It's filled with quantum fluctuations. Pairs of particles and antiparticles constantly pop into existence and then annihilate each other. These are called virtual particles. They borrow energy from the vacuum exist for about 10 to the minus 23 seconds, then pay the energy back by annihilating. Heisenberg's uncertainty principle allows this. The more energy they borrow, the shorter their lifetime must be. These virtual particles have measurable effects. They cause tiny shifts in atomic energy levels called the Lamb shift. The effect has been measured to extraordinary precision. Near the event horizon of a black hole, something different can happen. A particle-antiparticle pair appears right at the event horizon. One particle falls into the black hole, the other escapes. The particle that falls in has negative energy from the perspective of an outside observer. This is a strange consequence of general relativity near a black hole. The particle falling in reduces the mass of the black hole very slightly. The escaping particle carries away positive energy. To an outside observer, it looks like the black hole is emitting particles. The black hole is radiating. This is Hawking radiation, and it causes the black hole to slowly lose mass. It's evaporating. The rate of evaporation depends on the size of the black hole. Smaller black holes evaporate faster because the Hawking radiation temperature is inversely proportional to the mass. A black hole with the mass of the Sun would have a temperature of about 60 nanokelvin, 60 billionths of a degree above absolute zero. At that temperature, it would take about 10 to the 67 years to evaporate completely. That's incomprehensibly long. The current age of the universe is only about 10 to the 10 years. But a smaller black hole would evaporate much faster. A black hole with the mass of a mountain, about 1 billion metric tons, would have a temperature of about 100 billion Kelvin and would evaporate in less than a second, exploding in a burst of high-energy radiation. Now here's the paradox. The black hole eventually evaporates completely. All that's left is thermal radiation, random heat. Thermal radiation doesn't carry information about its source. It's like the heat from a fire. You can't look at the heat and figure out what was burned, wood paper or books. The heat is the same. This means the information about the book has been destroyed. The words, the ideas, the specific arrangement of particles that made up the book, all of it is gone, erased from the universe. This violates unitarity. It violates a fundamental principle of quantum mechanics. This created a deep conflict. Either quantum mechanics is wrong and information can be destroyed, or general relativity is wrong and black holes don't actually destroy information, or both theories are incomplete and something else is going on that we don't understand. For decades, physicists debated this. It became known as the Black Hole War. Stephen Hawking argued that information really is lost, that quantum mechanics breaks down in extreme gravitational fields. Leonard Susskind and Gerard 't Hooft argued that information must be preserved, that we just don't understand the mechanism yet. It's like throwing a USB drive containing precious memories into a furnace. The ashes don't contain the data anymore. The files are gone. The past has been erased. This isn't just an abstract problem. It's about the nature of reality itself. If information can be destroyed, then the past can be completely erased. History would not be permanently encoded in the universe. Events could happen and then vanish without a trace. It would mean that quantum mechanics, one of the most successful theories in the history of science, is fundamentally wrong. Black holes would be the ultimate document shredder. Even the NSA would be jealous. But in recent years, there's been a breakthrough. In the 1990s, physicists developed the holographic principle. The suggestion was that information isn't stored inside the black hole. It's encoded on the event horizon, the surface. Jacob Bekenstein and Stephen Hawking had shown that Black hole entropy is proportional to the area of the event horizon, not the volume. For ordinary objects, entropy is proportional to volume. A bigger box can hold more information. But for black holes, it's the surface area that matters. This is strange. It suggests that information is encoded on the boundary, not in the interior. The holographic principle extends this idea. The information in a volume of space can be encoded on the boundary of that volume. But this still didn't resolve the paradox. How does the information get out through Hawking radiation? In 1993, Don Page calculated what should happen if information is conserved. The entropy of Hawking radiation should initially increase as the black hole evaporates. Radiation is being emitted, carrying entropy away. But late in the evaporation, as more information escapes, the entropy should drop back to zero. The radiation becomes more and more correlated with what fell in. This curve showing entropy rising and then falling is called the Page curve. The problem was that nobody could explain how the Page curve could actually arise from the physics of black holes. For decades, the Page curve remained a prediction without a mechanism. Then in 2019 and 2020, there was a breakthrough. A series of papers introduced the concepts of quantum extremal surfaces and islands. When you calculate the entropy of Hawking radiation, you need to include not just the radiation itself, but also a region inside the black hole. This region is called an island. The island is correlated with the radiation outside. Here's the mechanism. Initially, the island is small. The entropy of the radiation increases as expected, but gradually, the island grows. Eventually, the island encompasses the entire interior of the black hole. At this point, the radiation carries all the information that fell in. Information is conserved after all. When you calculate carefully, including the island contributions, the Page curve appears naturally. The entropy rises and then falls exactly as Page predicted. It's like burning a book, but the ink somehow permeates into the smoke. If you analyze the smoke carefully enough, measuring every molecule, you could in principle reconstruct the text. The information isn't destroyed. It's encoded in incredibly complex correlations. The information doesn't escape in any ordinary sense. It's encoded in the quantum correlations between the particles of Hawking radiation. In principle, if you could measure the quantum state of every particle perfectly, you could extract the information. In practice, this is nearly impossible. You'd need to perform perfect quantum measurements on countless particles. But the point is that the information is there. It's preserved. Most physicists now believe the paradox has been resolved. The island calculations work in simplified models. They haven't been fully proven for realistic black holes in our four-dimensional universe. There are still details to work out, but the path forward is clear. The implications are profound. Information is conserved. Unitarity holds. Quantum mechanics wins the battle against general relativity. But both theories are correct within their domains. The resolution comes from understanding how they fit together, and the solution points in the same direction as our first question. Spacetime and gravity emerge from quantum entanglement. The fabric of reality is woven from quantum correlations. This idea, suggested by emergent spacetime, is reinforced by the resolution of the information paradox. Question 3 is nearly solved, and the solution tells us that black holes aren't document shredders after all. They're extremely powerful encryption devices so powerful that even the NSA couldn't break the code. The information is scrambled beyond recognition, encoded in patterns so complex that extracting it is practically impossible. But it's there. 3 questions, 3 mysteries, and they all point toward the same conclusion. So let's step back and look at where we are. We've spent this entire journey exploring 3 massive questions about space-time, 3 puzzles that sit at the absolute boundary of human knowledge. Let's recap what we've learned, and more importantly, what we haven't. Question 1. What is space-time made of? We don't know. We have 3 beautiful theories competing for the answer. Loop, quantum gravity, says space-time is woven from tiny loops, discrete chunks connected in a network. String theory says space-time emerges from vibrating strings in 10 or 11 dimensions. And the most radical idea suggests space-time isn't fundamental at all, that it emerges from quantum entanglement from correlations between quantum bits of information. All 3 theories are mathematically elegant. All 3 are logically consistent, but we can't test them directly. The energy scales involved are far beyond anything we can reach. Question 2. What happened at the Big Bang? We know the universe had a beginning. We know it was incredibly hot and dense. We know it's been expanding for 13.8 billion years. We have extraordinary evidence from the cosmic microwave background, from the expansion of space itself, from the distribution of galaxies. But the very first moment is hidden behind a wall. At the Planck time, about 10 to the minus 43 seconds after the Big Bang, quantum effects on space-time become important. Below that timescale, general relativity can't be trusted. We need a quantum theory of gravity, and we don't have one. Question 3. Do black holes destroy information? For decades, this seemed like an unsolvable paradox. Black holes evaporate through Hawking radiation, and that radiation appears to be thermal random, carrying no information about what fell in. But recent work on quantum extremal surfaces and islands suggests information is preserved after all. It's encoded in incredibly complex quantum correlations. The page curve emerges naturally when you calculate carefully. Most physicists now think the paradox is solved, at least in principle. Here's what all 3 questions have in common. They all require a quantum theory of gravity to answer fully. We're standing at a boundary. On one side, we have general relativity, Einstein's beautiful theory of curved space-time. It describes gravity black holes, gravitational waves. It's been tested thousands of times and has never failed. On the other side, we have quantum mechanics, the theory of particles and forces at small scales. It explains atoms-light electricity. It's the foundation of all modern technology, and it too has been tested countless times and has never failed. Both theories are spectacularly successful in their domains, but they contradict each other when you try to apply them simultaneously. General relativity treats space-time as smooth and continuous. Quantum mechanics says things are discrete and uncertain. General relativity is deterministic. Quantum mechanics is probabilistic. These aren't minor disagreements. These are fundamentally different worldviews, and they clash violently at black holes, the Big Bang, and the Planck scale. A quantum theory of gravity would unify these 2 pillars of physics. It would give us a single consistent framework for understanding the universe at all scales. It would complete a quest that's been going on since the early 20th century, and it would almost certainly reveal new physics, new phenomena we haven't imagined yet. History suggests that major unifications lead to technological revolutions. When Maxwell unified electricity and magnetism in the 1860s, it led to radio, television, and all of modern electronics. When quantum mechanics was developed in the 1920s and 30s, it led to semiconductors, transistors, lasers, and computers. When Einstein developed relativity, it seemed impractical, but today, GPS satellites rely on it. Nuclear energy comes from E equals mc squared. A quantum theory of gravity could lead to technologies we literally cannot imagine right now. If space-time is quantized, maybe we could manipulate it. Maybe we could create artificial gravity or control the flow of time. If wormholes can exist and be stabilized, maybe we could use them for travel or communication. If we could tap into vacuum energy, into quantum fluctuations, we might access unlimited energy. If the multiverse is real and accessible, the possibilities would be limitless. Now, these are wild speculations. Most physicists think it's probably impossible. The energy scales for manipulating Planck scale physics might be beyond any civilization's capability, but we don't know. And history shows that understanding fundamental physics often leads to applications no one predicted. Maxwell didn't invent the radio. Einstein didn't design GPS satellites, but their theories made these technologies possible. More importantly, understanding space-time would answer some of the deepest questions humans have ever asked. Where did the universe come from? What happened before the Big Bang? Will the universe end? What happens inside a black hole? Why does time flow in one direction? Why are there 3 dimensions of space and one of time? Why do the laws of physics have the specific form they do? These questions have fascinated humans for thousands of years. Every culture has origin myths. Every religion has grappled with these questions. Philosophers have debated whether time is real or an illusion, whether the universe had a beginning or has always existed. For most of history, these questions were purely philosophical. Science couldn't address them, but now we're close. We have mathematical frameworks. We have observational data from gravitational wave detectors and photographs of black holes. We have theoretical tools like the holographic principle. A quantum theory of gravity could tell us what happened at the Big Bang. It could describe black hole interiors. It could explain why time exists and why it flows forward. These aren't just scientific questions. They're existential questions about the nature of reality itself. There's also something philosophically profound about the possibility that space-time might not be fundamental. We experience space and time as the stage on which everything happens. Objects exist in space. Events happen in time. They seem like the most basic features of reality. The idea that they might be emergent challenges our deepest intuitions. It's similar to how solid matter is mostly empty space. When you touch a table, you feel it as solid, but the atoms are mostly empty space with tiny nuclei and electron clouds. Solidity is an emergent property from electromagnetic forces. The table isn't fundamentally solid. If spacetime is emergent, then distance and duration might be illusions in the same way. At the deepest level, there might not be any space or time at all, just quantum information patterns of correlation between quantum bits. Space and time would emerge from those patterns at large scales. This would be a radical shift in how we think about reality. The distance between you and the moon would be an illusion. The flow of time would be emergent. Everything happening now might not have absolute meaning. Past, present, and future might not be truly separate. This raises fascinating questions about time travel. If space-time can be curved, warped, can it loop back on itself? Einstein's equations do allow closed, time-like curves paths through space-time that loop back to their starting point. These describe rotating black holes and certain wormhole configurations. But closed, time-like curves create paradoxes. The grandfather paradox: if you travel back and prevent your grandfather from meeting your grandmother, you're never born. But if you're never born, you can't travel back. It's a logical contradiction. Some physicists suggest the universe conspires to prevent paradoxes. You try to change the past, but somehow fail. Or maybe time travel creates parallel timelines. You create a new branch of reality where your grandparents don't meet, but you came from the original timeline. Or maybe time travel is simply impossible. Stephen Hawking proposed a chronology protection conjecture. The laws of physics prevent closed time-like curves from forming. Quantum effects destroy the configuration before it can close into a loop. We don't know which is correct. We need a complete theory of quantum gravity to tell us whether time travel is possible or forbidden. Understanding space-time also affects our search for life elsewhere. If we understand space-time fundamentally, we'll know whether faster-than-light travel is possible. If it's not, civilizations are confined to their home stars. The universe would be full of isolated civilizations, never meeting, never communicating, except through radio signals, taking thousands of years. But if shortcuts through space-time are possible, if wormholes or warp drives exist, the galaxy could be connected. Civilizations could meet and trade ideas. The future would be fundamentally different. We're living in a special time. We're the first generation with tools to probe these questions seriously. We have LIGO measuring space-time ripples smaller than a 10,000th the width of a proton. We have the Event Horizon Telescope photographing black holes. We have particle accelerators creating early universe conditions. We have satellites mapping the cosmic microwave background with extraordinary precision. And we have mathematical frameworks that might describe quantum spacetime, string theory loop, quantum gravity ideas about emergent spacetime from entanglement. These theories are incomplete and unproven, but they represent a genuine progress. We might be close to a breakthrough, or we might be decades or centuries away. Science doesn't progress on a schedule. Sometimes breakthroughs come quickly and unexpectedly. Hawking radiation was discovered through a calculation meant to prove something else. The connection between entanglement and wormholes emerged from trying to understand the information paradox. Other times, progress is slow. Quantum gravity has been worked on for over 50 years, and we still don't have a complete tested theory. It might take another 50 years, or 100, or more, but the journey is worthwhile. The fact that we're asking these questions is itself remarkable. We're pushing the boundaries of human knowledge. We're trying to understand the universe at its deepest level. So let's come back to where we started. Space-time. Einstein's idea, the foundation of modern physics, an idea tested thousands of times and never failed, an idea we use every day in GPS, in our understanding of the cosmos. And yet, the fundamental mystery remains. We don't know what space-time is made of. We don't know if it's fundamental or emergent. We don't know exactly what happened at the Big Bang. We think we're close to understanding whether black holes preserve information, but details remain. This isn't a failure. This is the frontier of human knowledge. Every great idea eventually reaches a boundary where it can't go further without something new. Newton's laws reached that boundary with the speed of light and Mercury's orbit. Quantum mechanics and relativity reached it with black holes and the Big Bang. Now, we're at that boundary again, where Einstein's smooth space-time meets the quantum world. Somewhere beyond is the answer, a quantum theory of gravity, a description of space-time at the Planck scale, an understanding of the universe's beginning, maybe a unified theory describing all forces, maybe evidence of a multiverse, maybe something we haven't imagined yet. The physicists working on these problems are standing at a cliff's edge, looking into the unknown. They're using mathematics and creativity and centuries of knowledge to build bridges across the gap. Some bridges will fail. Some will lead nowhere. But one might reach the other side. And when it does, when someone finally figures out what space-time really is, it will change everything. It will complete the picture of reality that physics has been building for 400 years. It will be one of the greatest intellectual achievements in human history. So, the next time you use GPS, or look at a black hole photograph, or think about the Big Bang, remember this: you're looking at one of the deepest mysteries in all of science. You're seeing evidence of something we use, but don't fully understand. An idea that works perfectly in practice, but remains mysterious in principle. Space-time is real. We can measure it. We can photograph it bending. We can detect waves moving through it. But we don't know what it is. We don't know what it's made of. We don't know if it's fundamental or emergent. And that's okay. That's not a failure. That's where the adventure begins. That's where science happens. Not in the answers we've already found, but in the questions we're still trying to answer. Einstein gave us space-time over 100 years ago. It revolutionized physics. It explained gravity. It predicted black holes and gravitational waves and the expanding universe. It's been one of the most successful theories in history. But Einstein himself would probably admit it's not the end of the story. It's not the final answer. It's a step along the way. A beautiful, elegant, powerful step. But still just a step. The final answer is waiting. It's out there in mathematics we haven't invented yet, in experiments we haven't performed, in observations we haven't made, in ideas we haven't thought of. Someone will find it, maybe in our lifetimes, maybe in the next generation, maybe centuries from now. But it's there, and when we find it, we'll look back at this time, this moment, when we knew space-time exists, but didn't know what it was, and we'll see it as the turning point, the moment just before everything changed. Every time you look up at the night sky, every time you see stars scattered across the darkness, remember, you're looking at photons that traveled through curved space-time to reach your eyes. You're seeing light bent by the mass of galaxies stretched by the expansion of the universe, carried across billions of light years through the fabric of reality itself. You're looking at space-time, you're seeing it in action, and you're part of the generation that might finally figure out what it really is. That's the beauty of science. Not the answers we already have, but the mysteries still waiting to be solved. Space-time, the mystery we live in, the mystery that holds the universe together, the mystery that might be on the verge of being solved.